Let's go. No. Okay, cool. You see?
Yes, we can see. Thank you.
Okay. Hello again. Good afternoon, everyone. Today we will see a little introduction to performance monitoring. We will not go too much in details because that's the purpose of the next webinar. We will cover some general aspect about performance monitoring, focusing on x86 64 architecture. So what we'll see a little bit of introduction of HPC microarchitectures, and then we'll go for performance and efficiency of microarchitectures. Then we'll jump into other performance counters, a little bit of use of Linux perf, and then we'll see a naive roofline model and why we can use it, and at the end we'll see the conclusion of this presentation. Okay, so in an ideal world, an ideal CPU is something very linear, no? It's something scalar in order execution based on a reduced instruction set, 32-bit short pipelining, just one cache, uniform memory access. So something very cool to deal with. Okay, actually, from daily life, we can know that that's usually the contrary. On the right, you can see a representation of a Cascade Lake core, which is divided in front end, back end, and the memory subsystem. While on the left you can see a layout of the system of chip of the same microarchitecture. Currently, CPU are superscalar, out of order execution based with a lot of caches, complex instruction set, multi-threading, many cores. Multi-socket. So it's something quite complicated to deal with. So the question is how we can exploit performance on this system, this complicated system. No, the answer is maybe that depends about what you mean with performance of your application or the underlying system. No, maybe from a scientific point of view, you just focus on the result to be obtained by your code, and usually you want them in the less time as possible. Okay, but from a different point of view, maybe from the underlying architectural point of view, you would also need to be able to exploit the maximum from the underlying hardware. No, a common metric, for example, used in also to measure the top 500 list is the flops, which is the floating point operation per second. But there are also different metrics, and especially that's depend from what actually you want. No, but remember that it is always impossible, first of all, reach the theoretical peak performance. This is something we will see also in the roofline model. Is something, as the name said, theoretical. Okay, quite difficult to reach. I mean, and that if you focus and insist on trying to optimize a specific metric, maybe your effort can reduce other metrics. So we just have to deal with a mix of metrics and operation to obtain the maximum results as possible, both from exploiting performance and also from getting the needs of the scientists or people that run codes on HPC architecture. Just a few words about the difference among performance events and performance metrics. I mean, things like cycles, instruction retired, vector instruction retired, branches, cache misses, memory read and write are microarchitecture performance events, while metrics are composed by the metrics used, the events, and they can be, for example, the flops, the arithmetic operation executed, the memory throughput, the instruction per cycle, or the ratio of your vectorization. So that's to give a little bit of concept among these two things. However, although they are correlated. So as we have seen, it's quite difficult in modern CPU understand if and how my application is performing good or badly. No, I mean, we have seen that they are something quite complicated. Okay, and especially they change. No, if you move from architecture or microarchitecture to architecture or microarchitecture, you have to deal with different specific things to understand how you are performing poorly or bad or good. We need the support at least from the hardware to be able to read some useful information. The support is given by performance monitoring unit. Okay, sorry, someone has asked something. No, okay. And we can see here in this slide, and the next slide, you can see a little bit how it is composed, a performance monitoring unit. There are different performance monitoring units in your system, depending if you are in core or out core. Inside the performance monitoring unit, you can have PMC, performance monitoring counters, which actually are the counters read to obtain information of the events of your system. Performance monitoring counter can be at the same time fixed or configurable. Fixed, that means that they specifically measure some fixed events. They are a little bit easier to be read. For example, with read PMC, you can just read some specific fixed register. Or configurable, you can configure them in a quite complicated way, in a quite more complicated way than the fixed one, and measure them. Okay. Here we see a zoom inside a PMU, specifically an Encore PMU, but it's quite the same. And you can see that there are control register, which actually you can modify them, write the control register to decide what the counter register inside in each PMU can actually measure. Then you have some unit control status register for if you to check if you have some if you have to correct your result in the counters, no, because some counters have a 48-bit extension, someone else 64. That's depend. And then you have some free running counters that usually count some global events, and they are not modifiable. On the right, you can see a little list of the different PMUs you can find for the Encore parts, like the integrated memory controller, the U-box, the input-output controller, something like that. And depending in which of the box you are, you can access the program interface, so the control register, and get information from the counter register into different ways. Okay, but we will not dig into this specifically in this webinar. You can get information by model specific register, MSR, or by a PCI device configuration space. Okay. That's something that depends on the Encore part that we want to deal with. So we are starting to understand that it's not so easy task, no, to check how your underlying system is performing with running your application. But luckily, there are some software tools that can help us, and Linux Perf is one of them. Okay, it is the official Linux profiler, and is built on top of ftrace. It can provide you a plethora of tracing profiling features at all the system levels, and one of the most important thing is it has low overhead, comparing the time to solution of your code with and without it. Okay, that can increase if you turn it on or off the multiplexing. We are going to see just right now what it is. Here it is. There is a graphical explanation of the amount of events that Linux Perf can monitor and give to you. That's taken from Brendan Gregg pages. It's quite quite important for Linux Perf, but we are focused on the performance monitoring counters part. So cycle, instruction, branch, level 1, level 3 caches, etc., etc. Here an example of perf can be used in 2 different ways. Okay, from shell. Okay, and that's an example of how you can launch perf by bash. Okay, and so you use that to measure an application. Okay, with the -e you demand to perf to measure specific events. Okay, and the action can be sample or counting depending on what you want. So we said that perf can have a bigger or lesser overhead depending if you have multiplexing enabled or not. What actually is multiplexing? We have seen that on recent Intel architectures we have fixed, not on recent, in all the architectures we have fixed amount of performance monitoring counters. Okay, general purpose 8, fixed function 3, general purpose 8 if you have the hypertime disabled, so there should be 4 and 4 for each logical processor, and fixed function still remain 3. But what happens if you demand to measure more events than the number of counters that you have on each core? Then you have to enable multiplexing. No? So multiplexing give you an ideal final amount of the event that you want to measure using the math formula that you saw on the right. So the final count of an event is given by the raw count on the counter that you have, multiplied by ratio composed by the time enabled by the time running. Okay. So that can be from time to time quite precise, but from time to time not. So that's quite complicated from time to time using the multiplex, and you have to check, maybe double check your result in this if you have this option enabled. Another way in which you can use perf is actually calling the perf event open inside your code. Okay, so you're going to modify your code inside the perf event open, and then you have to pass it some specific attributes, especially in a form of a struct, and with that you can choose the type of the events. Now you can see type hardware, type software, type raw, depending of for each type there are a plethora of events that can be monitored by perf. Perf type raw is indicated, as you can read, a raw implementation specific event in a specific field of the struct that you can pass to perf event open. We'll see later an example. So okay, we have seen that current modern CPU are quite complicated stuff. We have hardware support to measure events and the right metrics from them, but to read these events is another quite complicated topic. So there are layers, cushions that enable us to obtain this info in a less difficult way. Okay, but once we have obtained this information, what we can actually do. Here you can see a classic naive roofline model. There are different roofline model. Here we can see just a naive roofline model, which actually give you an idea about how your code is performing based on the division of memory bound and compute bound. Okay. You can see the performance and the operational intensities as the axis of this graph. Operational intensity is the ratio of flops per byte. Okay, operational intensity, arithmetic intensity, that depends. And the idea of the roofline model is to give you also for example, I don't know if you have used the VTune of Intel, but the VTune can represent you, on a roofline model from running to running, how the point of your kernel, of your application, that's depending, move in this graph to give you an idea if you are if the optimization that you are applying are quite good enough to reach the peak performance of the system, or you are performing in a more bad way. Okay, so the idea is you can also draw it by hand, no biggies. And the idea is to reach at least after your your optimization, at least a better final point than the one from which you started your optimization. Here you can see a more beautiful roofline model representation, very cool. And here we report what we already said. Application kernel near the roofline model are making good use of computational resources. You can see. If you obtain bad performances, you have to check maybe some kinds of events or information like caches, bad locality. You have to check for a floating multiplier operation. So that's vectorization lacking. So you have to deal a little bit with your code. Here we report an example of the roofline model obtained with perf. So here we still dealing with the Cascade Lake system, okay? And on the left, you can see how if you go also in the performance events manuals of Intel, you can find the name of the events that you're looking for, and they are represented in this way. Okay, so on the left we are seeing the floating point instruction that we need. Okay, both in scalar and pegged. Okay, so if we are dealing with 64-bit or pegged, so we are using all the XMM, ZIMM, and YMM register. And on the right we have the memory read or write instruction. They are called cascount, okay, which are command issued to specify the address on the DRAM to read or write to, and then you have to multiply for the dimension of the cache line, and you get the number of bytes. However, there is a little problem. If you go to in the Intel manuals, you can see that, of course, these events are given to you by a combination of a mask and an event selector. They are hexadecimal value that you will need to be used in calling perf event open in those attributes of the structure that I saw you, that I showed you previously. But if we are going for the memory read and write instruction, for example, you can see that you have the event selector, the mask, okay, depending if you are going for the cast count read, cast count write, or the cast count all, okay. But actually, how we can change the channel for for each memory channel. That's that here is not reported inside the Intel manual. No, so it seems that we cannot change the channel, and for each channel we want to measure the cast count. No, you can see on the bottom right corner that for a cascaded system you have to integrate memory controller with a 3 channel each. Okay. So another solution is to check your underlying system, but in this case the software the Linux system. Okay, if you are going in the file system sysbus event source devices, you can find a plethora of events, and among them you can also find the Anchor integrated memory controllers, and the asterisk stands for from 0 to 5 because you have 6 channels. Okay, and the type give you a number. Okay, a number that you have to substitute on the right. You can see on this. You can see on the right an example of a C code. Okay, that you can substitute in the perf event attribute structure to be passed to the perf event open call function to actually read the event for which you want to know the amount of. Okay, in this case we were dealing with cast count, so the memory for the memory read and write. Quite easy, quite complicated. That's depend. I mean, there are people who want to deal with their code, and that's for them it's quite easy. There are people who don't want to spend too much time, and they prefer to use other tools that give it directly this information. That's why we just briefly present here Countdown, which will be the topic of another webinar. I don't remember, Laura, maybe the 4th or the 5th, I don't remember, but there will be there will be spent some other words on that. There are a lot of tools that give you information about how your code perform. Puppy, Liquid, VTune, as I said, and also Countdown, because Countdown is a project in collaboration among Sineca and University of Bologna, and we are currently developing it. So that's why we present it. And Countdown is quite easy to be used. You just have to compile it. You just have to export the LD preload variable for your pure MPI application, and then you don't have to modify anything of your code. Countdown will give you some information at the end of the run. Here an example of the final output, and I just report in the red rectangle some information with which we have deal all this presentation. And so you can see the memory usage, the instruction per cycle, the CPU frequency, the load cycle, the instruction retired, whatever, the flops in double or single precision, the memory data volume, the bandwidth, whatever, the vector ratio. Okay. Final slide. So no worries. I finished my conclusion, my presentation. Conclusion and takeaway messages. Of course, we can see that application workload have different performance on different architectures. But there are tools that can help you can help you on different architectures to understand effectively how you are performing, and models also can help you to understand in a better way the result obtained from the other tools. Of course, remember that tools can help you, of course, but you do the thinking. So first of all, think about what you need and what you want, and then use all the tools that you want. Something that I have shown you. I finished. Yeah, I don't know if there are some questions. I cannot see the chat. If not, I will leave the floor to Ondra. Otherwise, but I still